So my name is Rasmus. I'm a research engineer here at AI Sweden, focusing on decentralized learning for space and mobility. But today I will be giving you a brief presentation of one of our current projects, focusing on federated learning for autonomous vehicles. So in the last couple of centuries, or not the centuries, but 10, 20 years, we have seen a huge development in embedded resources and systems and electrifications of vehicles, specifically cars. And these cars are now becoming more and more digitized, equipped with complex arrays of sensors, cameras, and onboard resources for compute and storage tasks. And playing an integral part of our daily life, and also for across industries, cars are becoming more and more prominent for and potent for collecting vast amounts of data of our everyday life across streets and more. And with this data, we get unique opportunities for training more complex models that can help us in the development of future drive solutions. Of course, doing so, we also need to find a new type of balance between having a lot of data in order to get better models, get diverse models from using data across nations or across actors, but we also need to find out how much data we actually can manage with a feasible amount of resources and how to preserve privacy and not disclosing any sensitive information. So today, most of these AI models in autonomous vehicles are trained more using centralized pipelines. And as you all maybe know, then in this case, the vehicles collect images using these sensors and onboard cameras, where the data is then transferred to more centralized hubs for storage and compute. And here we usually see the integration of supercomputing facilities in order to facilitate the training process. However, this method also is seen now approaching a lot more challenges with respect to current and expected regulatory shifts in data transfer, especially international data transfer, but also data collection and privacy preserving. And managing these amounts of data is also very complex since it requires tight integration between different infrastructure across actors and across nations, which can induce costs and latency. But another way of doing this is using federated learning. So as you've seen in the previous presentations and also in the video, the core concept here is to move the modeling or the model and the training of the model to the actual edge of the system, in this case being the vehicles. So in this case, we train the models on board vehicles using locally captured data. So we get very specialized trained models on board the vehicles. But the case here is a bit interesting when we speak about autonomous vehicles, because we also need to evaluate how much of computational resources that the training actually requires to do this on board, and if and how this cooperates and interferes with other critical driver or safety related systems. So in this case, maybe it would be more feasible if the cars actually do the onboard training while the car is not actually in motion. So this creates unique windows of opportunity for scheduling training, much like how we do or how we see the communication constraints when we evaluate the application of space, or like satellites in orbit around space. But in this case, they do the onboard training, and whenever they are ready, they can then establish a connection to a centralized hub and move the model improvements rather than the actual collected images or sensor data in order to be federated into a global model that can then be redistributed to the system for further training. So in this case, we can then make the benefits of local specialized models while also getting more generalized models from the global aggregation. So by relocating the training of AI models to the vehicles themselves, we can ensure a more data privacy preserving mode of training, since we only communicate the model improvements rather than the actual images captured by these vehicles across the streets or different places. But we're also able to minimize the storage costs and optimize the use of compute, since we're now able to leverage the onboard resources from thousands of vehicles rather than having to be reliant on supercomputing facilities. And with these privacy preserving and also the use of distributed agents with limited or embedded resources, we can also be able to manage these huge quantities of data, benefiting from data from across borders or across actors, improving models and getting more diversity and general performance. So in this project, we aim to develop the edge learning technology to a level where it's ready to use for training AI models on board autonomous vehicles. And the idea here is to develop a framework that is both flexible and robust. It should be library agnostic with respect to federated learning schemes, use standardized communication protocols, which is quite new in this field, and also be scalable for future applications and drive solutions. And this framework will also be very essential for the participating companies, since it will enable them to define how to tightly integrate the federated learning system into current drive chains or drive solutions. It will also be very critical for finding out what type of hardware and requirements on data storage that is needed for doing this federated learning scheme. And it will also enable the companies to define and develop AI models that can actually benefit and make use of decentralized approaches. And working on this project, we're mainly 3 companies under a funding program of Vinnova. And at the core of this project, like all of our projects at AI Sweden, we're also working towards the UN sustainability goals, and where we see a lot of different applications, but most prominent being the efficient use of resources across vehicles and unique learning capabilities for future research. So taking a bit more deeper look into how we actually develop this framework, we start with a system setup with a hardware-in-loop environment using the Edge Learning Lab. And this is a very critical point, since we're able now to use the decentralized learning systems on board the Edge Lab, while also implementing it with industry-grade equipment. So in this case, we can actually simulate a more realistic onboard scenario of a vehicle. And this is also a very unique opportunity, and makes it possible to develop an initial architecture of this framework. The next step is scaling. So we move from simulating a single vehicle to actually using multiple compute nodes in the same hardware-in-the-loop environment, but now simulating fleets of vehicles to see what key challenges are here to be met and accounted for when considering multiple compute nodes. And the third phase of this project is especially interesting, and this is also where we are today, where we're taking a big leap, moving the framework from the Edge Learning Lab to a more realistic infrastructure based on Sensiact's development fleet. So in this case, we're moving the framework on board the vehicle to evaluate how the training of these AI models and the requirements of compute and local storage interacts with all of these safety and driver-related systems. And the last step, hopefully, there we go. The last step will be scaling again, where we consider doing federated learning across several vehicles and representing a smaller fleet. And this will also be extremely interesting, because will be one of the first real-life applications and evaluations on board vehicles using locally captured data and longer time sequences. And to work on this model or framework, we're using a verification process based on the holistic path model, which predicts the drivable path of the vehicle and using only images captured by the cameras and sensors. And the output is then the predicted path. And we can train this using Sensiact Open Dataset, which is a large multimodal dataset with thousands of images and sensor data, but also high precision GPS and various other technologies that enables us to develop derive a ground truth of where the car was actually driving and where the drivable paths are in the scene. But of course, as all of our projects here at AI Sweden, we're also aiming to generalize the know-how and the experiences we gain in this project to be applicable across various applications in different fields or industries. And this is something very interesting, since we're now dealing essentially with a system of distributed agents with embedded resources. And this is something you can see especially in healthcare, banking, and in space. So we aim to share our knowledge, but also gain insights from the other projects to further develop this tool for the future of transportation on board autonomous vehicles. And that's all. Thank you.